জুম করেছি
1x এর
বোঝা যাবে না কিছু বোঝা যাচ্ছে ভালো বড়গুলো ভালো না কে বলতো
थोड़ी देर बाद स्टेबल हो जाएगा।
वैसे वो जिसमें इशू है
Let's start. Good afternoon, everyone. Last year we started Lyapunov, right? So, what are the things we discussed? First of all, that is we revise the definition of the stability concept in the sense of Lyapunov. Then Lyapunov stability theorem for linear time invariant systems, right? And also the construction or the interpretation of the function v of x equals to x transpose vx, right? So if we just revise a little bit, v of x equals to x transpose vx. Now, how does it look like? Can anybody tell me? That is, how does it look like? So, for example, if I take a 3 by 3 case, then let's say this is x1, x2, x3, right? So this is like already transpose because otherwise the vector will be in a column vector format. And then p. Now what about this p? So it is like starting from p11, then p12, p13. If we take a symmetric matrix here, because ultimately, why can anybody tell me that it's always why do you or why do we prefer to take this p matrix as symmetric and positive definite? That too we discussed in brief. Can anybody explain a little bit? In your own words. That is why forming this energy candidate function, Lyapunov candidate or energy-like functions, why do we generally choose symmetric positive definite matrices? Two requirements, not only positive definite, symmetric positive definite. What is the requirement?
Dx is potential, so it's always positive.
That is first reason, right? That is like I wrote the three properties for a v function to qualify as a Lyapunov candidate. There are three properties, right? So first of all, what are the properties? That v of x equals to 0, that should be equals to 0, right? That means that is the system, and that is we are considering this as an energy-like function, or sometimes it can even become an energy function as well. So if the state goes to the equilibrium point, here we are assuming x equals to 0 is the equilibrium point. And what is the definition of equilibrium point? It is such a point where once the system arrives, after that there would be no further movement, right? So if you have a system, right, x dot equals to f of x, and now if your equilibrium point is x star, then that is what will happen, that is f of x star equals to 0 for all t greater than equals to, suppose ts or tf. TF means final time. That is, once the system reaches that point, after that there would be no rate of change of the state. And if the rate of change of the state is 0, that means there is no further movement, right? That is the definition of equilibrium point. And now this is directly related to the internal energy of the system. After reaching the equilibrium point, it is not able to move. What does it mean? It doesn't have any internal energy left. That means everything, whatever like potential it had, everything collapsed, right? That's why we assume this. That is, whatever may be the equilibrium point, v of x star must be 0. And here, for the class of systems we are analyzing, the equilibrium, yes, please. Equilibrium point, we are considering origin to be the equilibrium point. So that's why here that v at the origin, like v evaluated at the origin must be 0. Okay, this is the first requirement. the second one, that is what was that? It must be a positive definite function, right? So v of x must be greater than equals to 0 for all x belonging to D, right? Here this D means a subset of the whole Rn. Again, why this requirement is there? If it is for linear time invariant system, no doubt you can directly write for all x belong to Rn. But if it is non-linear, we cannot readily extend our analysis for the entire state space. So you have to do it for a region or a domain. That's why we are taking the concept of D. And here that is for all x belonging to D, this one, comma, x not equals to 0. Again, here you can ask that, sir, why you are excluding that x not equals to 0 here? Because if you consider x equals to 0, then you will lead to an ambiguity with the first function. That's why whenever if you check the definition of a positive definite matrix, then that is the x transpose Ax greater than 0 for all x in Rn, but when x not equals to 0, right? So that when x equals to 0, that is the trivial case where the function, whether it is positive definite or positive semi-definite, it will be 0. What I wanted to mean, that is, suppose someone wants to write the definition of a positive definite matrix, like suppose A, this one, or suppose semi-definite, this one, then how would you define? That is, for this one, positive definite matrix means x transpose Ax must be greater than 0 for all x. This backslash means excluding this one, right? And if you have to define the positive semi-definite, in that case what do you write? X transpose Ax greater than equals to 0 for all x Rn. Here, this part is not necessary. Why? Can anybody explain the difference? That is, here I have to use it, but here it is not necessary. Why?
Because x is equal to x transpose Ax is always 0.
Here you see it is greater than equals to 0. That means for some vectors it can lead to 0. Yes. So here it can happen. That is, what does it imply? Definitely there will exist a vector in Rn which is not identically 0 such that x transpose Ax equals to 0. And of course, for x equals to 0, x transpose Ax equals to 0, which is the trivial case. Everyone must be careful about these two. And this one, the first one, that is the main difference between a positive definite matrix and a semi-definite matrix. The trivial case, it will come here as well. And that is the reason why in the definition of positive definite, we have to exclude the origin. I mean the x full null vector. Please take some time to digest it. The difference between positive definite and positive semi-definite. These are small things but very important things. Sometimes why we get confused, because in most of the books these nitty-gritties are not written. That is the difficulty. If you see any book on matrix algebra, other things, of course you will find plenty of like the examples and the theory, everything, but this kind of small ingredients generally are not written because authors often think that like, these are so trivial to be mentioned. Is it now fine? Is it fine for everyone? Any doubt? If you are confident with this one, then I believe you are sure about that is why I have excluded x0 here, right? And now what was the third requirement? That is this rate of, first of all, this v dot should exist. It must be continuous, like what I wrote earlier, that is v dot x lesser than equals to 0. Given you asked that is it should have been negative definite, right? That you were asking when I wrote the Lyapunov stability theorem for the LTI. This is at least, that means the minimum requirement. Now under which, that is that day I didn't have any more time, so I didn't mention. Under this you will have two cases. One is really positive semi-definite. Another case is that positive definite. Sorry, negative. Negative semi-definite and negative definite. So the case of this lesser than equals to 0, semi-definite, that you can consider a superset, under which the case of strictly definite, I mean the negative definite, will also come. So these are the three main characteristics of a V function to qualify as a Lyapunov candidate function. I repeat, these three properties are required for a V function to qualify as a Lyapunov candidate. Okay? Now, the moment that is I wrote this one, v dot x lesser than equals to 0. Now, before I write v dot x, I'll have to ensure whether v dot x exists or not, right? So that's why that is I considered, so this v function, when you construct a v function, it must, its derivative, like v dot, it must exist, right? It must exist and it should be continuous, because if it not continuous, then you cannot express it like that. Because when you are writing this, we are not putting any constant on the x. So that is whatever x you take, that is it must satisfy this condition. So that's why that is the moment you write this, implicitly we are assuming that is v dot of x, it exists at least in that domain and it is continuous. Okay? Is that fine? And then what is my v dot of x? That too we have defined, that means it is the total derivative of the v function. So total derivative means ddt of v of x. Now if you apply the chain rule, then what will happen? That is now x is again a function of t. So that's why first you have to make del v del x and then take the differentiation of x with respect to t. So del v del x into x dot, right? And so that is del v del x, and now instead of x dot you can write fx. Please note that del v del x you have to write in a row vector format, del v del x1, del v del x2, like that, and this fx it would be in terms of like x1 dot, x2 dot up to x7, right? So this one is a column vector, this one is a row vector, ultimately it is like an inner product, so that exactly lastly we will get a scalar product, because both v of x and v dot, they are scalar functions only, right? And this particular form, x transpose px, this is called the quadratic form, right? So both vx and v dot of x, we expect those to be written in quadratic form. Up to this much, is it clear for all of you? Now, coming what we were originally discussing, that is why this function we take symmetric and positive definite. So energy function or energy like function, that should always be at least positive semi-definite, isn't it? Do all of you agree with that? Like the energy of a system, whether it is internal energy or energy being received from outside, it cannot be negative, right? At minimum, it can become zero or else positive, right? So that's why the requirement is that is this energy function d of x, it must be greater than equals to 0. That is at least. Please don't get confused between the greater than equals to 0 and greater than 0. the minimum requirement is positive semi-definite. Okay, and immediately we'll ask that is, sir, then why that is all the books they start with that Vx positive definite, immediately that query will come, right? That is, if I say the minimum requirement is positive semi-definite, then why to consider positive definite? Because that is slightly a restrictive class of functions, right? Now can anybody tell me that is what is the requirement?
Because if it is already, if V of x equals 0 already, then we don't need to apply the stability theorem because its energy is already 0, so it cannot decay any further. So already at equilibrium point, you should say.
Or other, suppose like if you consider the energy to be positive semi-definite, then of course at the equilibrium it would be 0, and then the difficulty of local minima points will come into the picture. Say for example the trajectory is going something like that, then although it is not 0 but it is a minima which is called a local minima, then at that particular point also that is V will be 0. Then that is, it will create a lot of confusion whether the system has arrived equilibrium point or it is stuck in a local minima. This ambiguity arises if we consider semi-definite V. Are you getting? That is what I said, that is a V of energy function that is only at the equilibrium point it must be 0. But if it becomes 0 at some other values of x, then which are those x where temporarily the system, like temporarily the rate of change of energy or the energy becomes 0. But certainly there it is, for such kind of point you will see, that is, suppose this is xf, you will find that V of xf that is equals to 0, but V dot of xf not equals to 0. Such situation can also arise if it, especially if it is a local minima. Local minima means for some time somehow the system will reach that point, will stay there for some time, and then it will move away.
So basically like a saddle point.
And because of these local minima problems, all these meta-heuristic algorithms, like those who work or know about this AI or ML, most of their algorithms are meta-heuristic algorithms. Say for example, genetic algorithm, PSO, and most other. That is where, that is, we don't have a proper theoretical formulation that works first of all for a favorable initial condition and then based on different type of condition and assumptions. So there people faces this kind of difficulties, that is sometimes it gets stuck in the local minima. And when you run a very big computer program, maybe after 2 hours you see the program is like it is coming to the end saying okay, the minimality or optimality has reached, but when you really check you may find that is, oh no, that is not the real optimal point. This is a local minima, not the global minima. So for that reason we consider positive definite function. That is, if the energy becomes 0, it will enable you to command that is okay, the system has already reached the equilibrium point, not somewhere stuck in any other point. Is it clear for all of you? You take your notes, you there is write in your own words. Okay. If you have any doubt, please feel free to ask. বিমলজি কেমন আছেন? অনেকদিন পরে দেখা হলো। এই আজকে ক্লাস নিচ্ছি। ক্লাস নেই, এই সেমিস্টারে খুব লোড চলছে। This quadratic form I am going to write on the other side because in between that is we discussed all these things. So far, is there any conceptual doubt? At the beginning, there is I am trying to develop your theoretical foundation, and then later when we'll solve the examples, then everything will be okay. Why I always emphasize on the theoretical foundation, because if your the theoretical concept is sound, then even from the books also you will be able to understand the examples. Otherwise, what happens, that is, if you directly jump to the example to understand many points, you will not be able to understand. That is the problem. So that's why I always spend like sufficient time, that is, on the theoretical analysis. And later also it will help you to, when, that is, suppose for the MTech people, when you will like start your MTP, for the PhD student, when you will read papers, even for the MTech students also, in your like second year, you will have to read at least a few papers for your like solving your MTP project. Then, as you know, that is, in the papers, it is not like a book, maximum 8 pages or 10 pages, where most of the things are written in a mathematical fashion. The text representation is really very less. So that's why that is all control people, or they will be those who go for theoretical studies. At the beginning, we face a lot of difficulties in understanding from the papers. So that's why I always try in all of my subjects to deal with the hardcore level of mathematics and the theoretical studies, so that later you will start reading any high level book or journal papers, you don't face that much of difficulty. Like you see, this kind of notations, when I first started at the first year of my PhD, that is, it took a lot of time for me to understand even the notations. It is not that it is tough, but unless you know the exact meaning, you cannot like understand the concept of the actual thing, right? So that is the main problem for all control students. Not only control, they can control theory, communication theory, signal processing, everyone the same thing, because they are all mathematically intensive. Anyway, just coming back to the V dot, what I was explaining, that is under this requirement, so this is the minimum requirement, that is V dot of x is lesser than equals to 0. Now again, that is the same kind of question I can ask, that is why this requirement. Whatever you have understood so far, please tell me, that is why we have just discussed, that is what is the requirement for this V function to be at least positive semi-definite, but it is better if it is positive definite. That reason we have discussed, right? Similarly, what is the reason for considering the V dot to be negative semi-definite and the preferred is negative definite? Once again, that is negative semi-definite is the minimum requirement, and the negative definite is the best for us. Please try to explain. Same thing related to the energy concept only. Now earlier we discussed that is the energy content V of x. Now V dot means rate of change of energy.
Non-zero term, it can be horizontal. So there V dot of x will be 0, but V of x is always greater than 0.
The same thing is like the point of, like, suppose if there is going like that, then it is now what happens, that is, suppose V dot x, it is at a particularly, suppose at this point, that is the V dot x equals to 0, but here just the opposite case, V dot x equals to 0, but V of x is not equals to 0. That the local optima problem, right? Have you understood? Now the first question is that why that is we are so much obsessed about V dot. That is the first question. Why do we like that candidate so much?
Otherwise, you cannot tell if the energy is decaying or not.
That is V dot means rate of change of energy, right? Now you see, highly related to this point, this Lyapunov stability analysis is mostly for unforced system. Can anybody relate this fact? That is why do we consider an unforced system in this respect?
Because we are checking only the internal dynamics of the system. We cannot checking if we give an input from the outside, like external input from the other system, and then we cannot check if it is actually decaying or not. If it is only, if V dot x even becomes 0 or less than 0, then also maybe the system will go on.
Exactly. Patri, can you explain this point? Can you elaborate?
if we keep the external forces like that,
Huh.
then we can foresee minimum or maximum the energy. But we are checking for the only internal dynamics whether it will stability decaying or not. So it's better for unforced. That's why we are.
In simple words, suppose you have the system H dot equals to Ax plus Bu. So this is your force system versus you have your X dot equals to Ax and X0 not equals to 0. This is your unforced system. Okay. Now Lyapunov stability analysis says that it is completely, the concept comes from physics and we are bothered about whether the internal energy is decaying or not, right? Now if you already have an input term, so you are already pumping some energy into the system. So then, that is even after that, if V dot X is less than 0, then we cannot readily say that it is asymptotically stable. That is the problem. When you consider an unforced system, so what is your internal energy? That is the V of X is X0 transpose Px0. That is your internal energy. So with this much of energy, the system will start moving. This is highly important. Please try to understand. That is, for an unforced system, initial condition is non-zero. Again, that is a small point. Why you have to take initial condition non-zero? Otherwise, like already you are considering an unforced system, and on top of that, if the initial condition is 0, that means it is already sitting on the equilibrium. So there is no rate of change and there is no movement. You cannot analyze the stability of the system, right? So that's why we take on the initial conditions. Now, that is when you test unforced system, but which is you are going to analyze an unforced system which is not on the equilibrium point, then it has some finite internal energy. How much is that? X0 transpose Px0. Okay. Now from that is if you can ensure that is V dot of X is less than 0, then what will happen? Suppose at this moment, like this energy, what is the unit of energy? Joule or what? Joule, right? Suppose that it has energy 10 joule. Then, if V dot X is less than 0, then what will happen? From 10, exactly it will be 9, 8, 7, ultimately it will reach 0. That is nothing but the concept of stability. Everything comes from physics only. Right? Now, that is if it is lesser than equals to 0, then what can be the problem? It may happen, that is maybe after reaching 4 joule, it has reached a local optima and then it will get stuck. It will give you a feeling as if the system has reached the equilibrium point, but which is not. That's why that is we always that is the V dot X, the negative definite case is preferred for us. But at the same time, you must know that not for all type of system we can find a V function whose derivative would be negative definite. That is the main challenge. Once again, although the V dot X is less than 0, that is a negative definite V dot, is the best for us, that is for a given system. What is Lyapunov analysis? Given a system, you have to first form a V function, that is which will satisfy these properties. Now coming to the third one, that is the minimum requirement, that means it has to be negative semi-definite at least. But if you can find a V function which is negative definite, then you can become, that is like excessively happy. That is okay, our job has reduced to a great extent, right? But it is not always possible, especially for nonlinear systems. For LTI systems, we can find that, because for most of the LTI system, X transpose Px is the best candidate, and for such construction, the V dot of X also mostly, in most of the cases, you will find that it is coming negative definite. But for nonlinear systems, getting a negative definite V function is really, I mean, that is the some very best cases. Okay? Have you understood the problem? Now that is if it is negative semi-definite, then that is what you can conclude. Negative semi-definite means that is actually the energy is either decaying or at least it will remain constant. There is no chance of increasing the energy, right? that means the system is considered to be stable in the sense of Lyapunov. Once again, if your v dot of x less than 0, negative semi-definite, what does that mean? That means your internal energy is either decreasing or it after some time it has remained constant, but at least it is not increasing, right? So if the energy doesn't increase, what is that case? Marginally stable, right? So if it is 0, then we call that kind of system is just stable in the sense of Lyapunov. Now, from our basic concept, under when we say just stable, under these two cases will come. What are they? One is asymptotically stable, another one is marginally stable. Usually, that is what in the Lyapunov literature they don't mention marginally stable. This case they write bounded trajectories. Stable means bounded trajectories. Okay. In short, I am writing. Are you getting? That is, if the energy is not increasing, then what does it mean? That is, system is stable at least. So marginally stable means kind of either a sustained oscillation or something like that. So at least the trajectories will not grow in time. Okay. So that's why they mention bounded trajectories. Okay. That is called stability. Now under stability, these are the two cases. Immediately somebody can argue that is, sir, why are you saying that is asymptotic stability may also come under this, because you are already saying that it is negative semi-definite? Do anybody has a similar thought? That is, I said negative semi-definite. If it is so, then the energy can either decay or after some time it may become constant, right? But do you agree that the asymptotic stability will also be a subset of this? Do you agree? It must be, right? But where is the fallacy? That is, what is the connecting point? Negative definite is a subset under negative semi-definite. That is the reason. In many cases, you will find that if we are not able to find a v function whose rate of change is negative definite, but that is our problem. Suppose that is for a nonlinear system, we all have been trying to find a v function whose v dot will be negative definite, but suppose none of us is able to find such a v function, but maybe another smarter person can find such a v. That is one of the problems with Lyapunov, because this v function is not at all unique. It depends upon experience, how better v function we can find. So for a system, if you are unable to find a v function whose derivative is negative definite, that doesn't mean the system cannot be asymptotically stable. Please be confident about that. Once again, if you can't find a v function whose dot is negative definite, that doesn't imply the system cannot be asymptotically stable. Why? Because someone else may be able to find a better v function whose v dot would be negative definite. Okay, so that's why when you get a v whose derivative is lesser than equals to 0, that is negative semi-definite, it can become negative definite. So that point is really critical. You will immediately ask, that is, okay sir, under such cases really we are not able to judge whether this is marginally stable, I mean the case of only bounded trajectories, or really it is asymptotically stable. How to break that ice, or that is how to take the decision there? Any idea? That means I am asking, that is for such kind of cases, that is where you cannot find a v function whose derivative is negative definite but negative semi-definite. Under such cases, can't you analyze the asymptotic stability? That means, are we handicapped that after saying bounded trajectories we cannot go further? Is it like that? It shouldn't be, right? So what are the techniques which we must apply in such cases?
Can we say like it is locally asymptotically stable?
Even for locally asymptotically stable also you have to get a negative definite function over D. I was about to write the theorem, but before that I thought of describing everything so that you can understand the theorem well. So what Auditory you said, that is correct. That is when you are saying, when I said V dot x is less than 0, that is for all x D, that is not over R, okay? And this is not identically 0. V dot x when we are in the Lyapunov in most of the cases, because now in this case we are whatever we are learning subject to a nonlinear system. So you don't think that is now this Vx or V dot of x, they are defined for the whole array. Up to the last semester where we dealt with only LTI systems, there your V function or whatever you take, that is spread across the whole array, but here it is always D, okay? So this stability or even asymptotic stability, whatever we are concluding, local, please don't get confused with that. So even for local asymptotic stability, you will have to show negative definite V function. But if you can't find such a V function, then how to conclude? That is, are we handicapped under such cases? That is, no, we cannot analyze the asymptotic stability. It shouldn't be, right? So under such cases, what we can do?
Then apply linearization technique and non-linear.
But as you know, in the linearization also, that is, we have some problems, some issues. So here what we can do? The easier technique is you try to find a better V function. That is the easier technique. And second one, which is the most authenticated technique, is Lassalle's invariance principle. You might have heard the term. Lassalle's invariance principle. I think he was a French mathematician. This is about the overview, okay? Not overview, actually, this is the core thing that we are going to learn, but in a nutshell, I have described everything. So that immediately when I will write the theorem, you won't believe much trouble, I believe.
Sir, could we use multi-heuristic algorithms?
But there you don't have the guarantee of reaching the optimal point. I mean global optimal point. That is the main problem. All these meta-heuristic algorithms, they can also reach some optimum point, I mean the minima, but not guaranteed whether it will be the global minima. In many cases, they reach the local minima, and that's why these days when they write, they never claim exact optima or exact optimal, they write suboptimal. Is it now fine for all of you? So, under these negative semi-definite cases, how to resolve the thing? Either you change the V function, or if you can't, then you apply Lassalle's invariance principle. Okay? So, don't worry at this point, that we have to, we will run, that is how it works. But for that is first I will show you a quadratic form, a simple example from Collin's book, then I will write the Lyapunov stability theorem. Up to this much, is it fine? Please check your copy, and if you have any doubt, you ask. The example which I am going to write, that is for Khalil's new book, Global Addition. It is example 3.5. Okay, you can write that is example 3.5, page 62. I think it's scan copy I uploaded at the very beginning. Okay. Why I am taking the example from the book this time? Because so that later you can see it easily, and then you can like write the full description. You can learn the full description. So here what they have written, ax1 square plus 2x1 x3 plus ax2 square plus 4x2 x3 plus ax3 square. Let us verify. Ax1 square plus 2x1 x3 plus ax2 square plus 4x2 x3 plus ax3 square. Right. And now that is your job is to represent it in the form of x transpose px. Okay. Please try to do that. That means here you must write x1, x2, x3. So that is my x transpose. In between, you should have a 3 cross 3 matrix which will serve the purpose of P, but what kind of P, that we don't know. That we'll have to analyze, that whether it is positive definite, positive semi-definite or indefinite, that we don't know. But you have to, that is the reason why you have to first express that in that fashion. That means this is called a quadratic form. Everybody please look at the board just for 1 second. When you see a function expressed in this form, this is called quadratic form. Why? Because you have some quadratic terms on there, or even for the coupled terms, you see it is a product of two states, like x1 into x3, x2 into x3. Okay, these are nothing but a quadratic form, and any quadratic form can be expressed in x transpose px format. Okay, from that the name has come quadratic form. Here you must not have any cubic term. Okay, so now can you please tell me that what this matrix is going to be?
A01,
Right? A01,
082,
0A2.
128.
Right, very good. Can you also find out the condition on A such that it will become positive definite? Just a small hint, that is what is the first principle approach? That is, you take this whole matrix and you find the determinant. From that you can like with eigenvalues, right? So that is the first principle approach. But there is a shortcut. What is that? Eigenvalue, then you have to find everything. Shortcut approach is that leading principal minors. Leading principal minors means this A, that is the minor with order 1, minor of order 2, and the minor of order 3. So what I wanted to ask, that is for what values of A, P will be a positive definite matrix, or at all it is possible. So first of all, you see from there it is already, that is A has to be greater than 0. Here also the same thing, A greater than 0, and then from that maybe you will find a term A square minus 5 has to be greater than 0, isn't it?
So mod will be greater than root over 5.
Exactly. So for that range of A, this function is going to be positive definite. Okay, that is the concept of quadratic function. This is just an example. You can see that is here also the same thing is written. The leading principal minors of P are A square and A into A square minus 5. A square and A into A square minus 5. Therefore, Vx is positive definite if V is greater than root 5. Okay. Simply that means we are trying to find out that is whether this P is positive definite or not. The first principle approach is that you find the determinant and check that is when, ultimately the positive definite matrix means the eigenvalues would be positive. So for what range of A, it will have positive eigenvalues. Okay, that much only. Now the most important part, we have now stability theorem. Then how to start? Last day we were discussing, right? So that is, yes, the first we have to start with the supposition. Then it is all of you think and you suggest me, that is how should I start? You just kindly go back to your last class note and check what was the definition. In the same setting we have to start, right? Because in the last day we defined only the concept of Lyapunov stability. Now it is Lyapunov stability theorem. So the supposition, especially I believe the first two lines should remain the same, isn't it? Or what was the first line?
F of x be a locally Lipschitz function over a domain.
So here our system is x dot equals to f of x. Okay. Now whatever analysis we are going to do on this fx, right? So that is like for this Lyapunov stability analysis, this differential equation and this nonlinear differential equation must be solvable, right? Or its solution x of t, it must exist and it should also be unique at least for some t. Otherwise, we cannot apply the stability analysis, right? So that's why that locally Lipschitz condition that we need to impose. Like, but yes, so far we haven't discussed the Lipschitz continuity. We will do that because it is related to some mathematics, so that's why I am not directly bringing here. For the Lipschitz, I will take a full class because the concept is little tricky. I shouldn't say tricky, but I believe it is new for all of us. So that's why that is I need at least 2 hours for that. Then, Arindra, tell me, what should I write? Let
f of x be a locally Lipschitz function over a domain.
अरे देख के क्यों बोल रहे हो? देख के अगर लिखना है तब तो मैं बुक से ही लिख सकता था. Let fx be a local, right? You should not write global. That's why there is I am putting an underline under locally because it is very important. Let fx be a locally Lipschitz function over a domain D which is a subset Rn. That contains, that is if we that region D must contain the equilibrium point, otherwise for whom we are going to check the stability, isn't it? That is the requirement. That contains the equilibrium point x equals to 0. in bracket you write that is f of x star equals to 0. One second, Monica. That is here in bracket you write unique. Right, thank you. Not then, because in case of definition we didn't have any other things to assume. Now, that is before we proceed, we have to take that p function, right? That's why we need one more let. Are you getting? That is, you please compare with the definition. In the definition, this was this entire supposition. After that, I wrote the exact, like the definition part. But now we are going to write the Lyapunov stability theorem, which needs a v function. But then we have to introduce the v function, right? So that will make your second line.
Write the 3 points of v of x.
No, v of x. Oh, we were asking for those 3.
Yeah.
That is, let's see. That is, first we have to consider a Lyapunov candidate function v of x, and then that is like one by one we'll have to write the condition when it would be stable, when it would be asymptotically stable, and then when it would be globally asymptotically stable. Okay? That's why it is a bit lengthy, but we should understand that is how we can write it without looking into anything. Can you tell me the second line? Why? Okay, the second line for what? Try. I didn't say that is, if it is wrong, I will give you a punishment. Let what does that mean? V is a function of x, and then it maps x belongs to Rn, so its domain is Rn, and it's a scalar function, and its range is the positive half of the real line. That is the meaning of such a function, v of x colon Rn to R plus, right? Let v of x be an energy-like function और एक बार सुनाई नहीं दिया
That is continuous at first derivative.
हाँ, उसमें भी एक समस्या है with v of 0 equals to 0 and v dot of x now that is what you wanted to say. Same thing last day solution was said. In some books they wrote that is instead of v dot x being continuous, they write, even you also said the same thing, with first partial derivatives, right? Now are they equivalent or there is a glitch? the real analysis book, you will find that this is like if there is all the first partial derivatives are continuous, even after that v dot x may not be continuous. Because here, not only here, you have the x dot component as well. This is the total derivative. So if v dot exists, immediately that will imply that is all of them exist, they are continuous, but not the vice versa. There is a theorem that even if all the first partial derivatives exist, but v dot may not. So that's why the exact technical term is that is v dot x being continuous instead of saying the first partial derivatives. See, for linear time invariant system, it doesn't create any problem. Both of them are equivalent, but when you are dealing with nonlinear system, then comes the problem because this x dot is also there. Are you getting? That is v dot of x. It not only depends upon del v del x, it depends upon x dot as well. Now, if it is LTI, that x dot is simply a of x, which is a linear function. It doesn't give you much headache. But if it is nonlinear, that is your f of x. Here, very bad type of nonlinearities may also be there, which can cause a trouble. Right. Now, after this, okay, tell me, the first one, that is the easy one. About this stability, what should I write? So समझ के बोलो, ठीक है? Next one नितिशा will say, and उसके बाद सवाल है। How to write? Okay, जो technical writing हम लोगों को सीखना है, इसीलिए मैं इतना कोशिश कर रहा हूँ. Otherwise, I could have simply wrote the things. So here you can see two lines, they are our supposition part. So the assumption, everything is now like covered. Now the first result we are going to write, the condition for the stability. How to write? The equilibrium point or the origin is locally stable in the sense of Lyapunov if. That is the style, right? Here we have considered the origin to be the equilibrium point. That's why I am writing the origin. Otherwise, you can write the equilibrium point x star equals to 0. That is the full sense, like the full expression. The equilibrium point x star equals to 0. Since I have considered here the origin to be the equilibrium point, that's why I am writing the origin is the origin is, again here is a question that is like we know locally, then why I am putting in the bracket? Some of you may think that this sir is unnecessarily complicating the things. Why?
Because v dot x can be negative similarly.
No, that is fine. But here, if I have to put it locally, then why I am keeping within the bracket? Why I am not writing without the bracket?
Because we are taking in a particular domain, not in the all Rn space.
But here, when we write and say that v dot x
Be continuous.
actually in the statement already that region is included, D. So that's why even if you don't write locally here, it will be implied locally. But still I am writing locally. So that means it is redundant but very important because somebody can miss. That's why I am putting in the bracket. Are you getting my logic? When you are writing it is over the domain D, that means already whatever conclusion we are writing, that is for locally, for sure. Then it is not necessary to write locally again, but still I am writing, so it is a redundant term. That's why I am putting in the bracket. Second question comes, sir, if it is redundant, why you are writing? To emphasize, so that no one should miss. Yeah, doubt? Fine? Everyone, have you got my point? So here, what I think I should, what I missed, I think it would be clear in a sense if I write something more. And v dot x exists and is continuous over the domain D, okay, containing x star. Containing x star. Now it is complete. Can anybody tell me what I missed? That is, what is the difference between this and what was earlier? I didn't mention the domain restriction on v dot. I mentioned the
X star is redundant, I think. Before the domain D that contains equilibrium.
okay. That is also fine. This is again in my it is redundant, but still I would to give some emphasis. But anyway, you are correct. That is, here we can skip, no problem. So the difference with the earlier version is that I didn't impose the domain constant on the v dot function. The domain constant was already there on the v, but that is one requirement. But the second requirement is on the v dot also we cannot write as a global function, right? And now, is it clear? That is why I put locally in the bracket. That means it is implicitly understood that local stability, but since it is a very important point, to emphasize it once again I am writing, and that is the requirement why I put bracket. Now you can answer, sir, if I don't put it bracket and if I write local, then how do you read out? The origin is locally asymptotically stable. Immediately it will then like find redundancy, like mismatch. That already it has been, the function has been defined over D, and again here we are claiming local stability, then there is some ambiguity. Have you understood? That is the reason why I am putting the bracket. Please take some time to understand. If you have any doubt, ask me. तुम लिखो मत, तुम बोलो इसके बाद क्या होगा. The origin is stable in the sense of Lyapunov if
v dot of x is less than or equal
X.
that is, it is the case of
negative symbol.
Asymptotically stable.
no. First one only stable, that is BT case, bounded trajectory. So v dot of 0 lesser than equals to 0 for all x belong to D. Now आलिन कैसे बोलोगे है? All x belong to D. And here what should you write in the case of negative self-definite? So including the origin. I put a semicolon because this is not the end. After that we have to write 2 more. So are you getting? Everyone, any doubt up to this much? Next one, Nitisha has to tell. Asymptotic stability part. If someone wants to come on the board and write, then please welcome. Or would you like to come on the board and write? बताइए? Okay.
हो गया मेरा.
Oh, अच्छा. Try. See, class is the best place where you can practice, because here I am not judging you. We all are learning. You are learning, while teaching I am also learning. So don't feel any hesitation. If you don't reveal your concept, that is of course there we have some limitations. So it is impossible for a human being to know everything in a correct manner. Unless you say those things, I cannot help you to correct. Bolo.
The equilibrium point is asymptotically stable.
The origin is locally asymptotically stable in the sense of Lyapunov if
V dot x less than 0 for all small x that is subset of capital X belongs to capital D.
फिर से इधर कैपिटल एक्स कहाँ से आ गया? Only D and then suppose capital X नहीं है, D is the domain and then after that
क्या बोला मैंने? For all small.
so the second one, Auditro, can you repeat what she said?
The origin is locally asymptotically stable in the sense of
Origin is, again I have to write in bracket, origin is locally
asymptotically stable.
Sense of Lyapunov.
If V dot x less than 0,
That is negative definite case, so we have to remain
for all x not equal to 0.
exactly. That is the main important point which you missed. That is for all x belonging to D. Now you have to exclude the origin, but where in the first case origin was included, right? You can answer this, sir. If it is asymptotically stable, then anyway the last point would be V dot equals to 0, right? That is also there. So if this one and V dot of x equals to 0.
X star.
X star or
X. V dot X star.
That is this one. It will imply that because it's a positive definite function, right? You see, that is in good point, good one. You were, that is what the doubt you had, I understood. Here you see what is this meaning? That is from Rn to R plus. That means here it is already said it is positive definite. Because if you consider the V function to be positive semi-definite, then it doesn't imply that is V dot of x 0 means that is when I write it, then this is implied that x is equal to x star, and this implication is true only when you declare the V function to be positive definite.
R plus. Then you should add a R plus union of 0.
Yeah, if it is positive definite, that is for all non-0x. Or rather, that is that if you have problem with this, then someone can directly write let V of x is a positive definite function, is a positive definite energy like function with this.
So I have the same doubt. So does R plus is
Huh.
include 0 or we have to include 0 separately?
That's just about
R plus generally that is includes like not doesn't include 0. Okay, so here that's why in see there are that is also an important point. Some authors use R plus to indicate that is all positive real numbers including 0. Okay, and some use this like this one versus another notation is there R double plus. That is why it is strictly positive. It is like inclusive of 0. But here I didn't use in that sense that inclusive of 0. Then you can ask that sir, how then you consider the 0 case? That's why I wrote separately V of 0 equals to 0. So if you have some confusion with the notation R plus and R double plus, simply you can write R greater than equals to 0 or even R strictly greater than 0. I believe that this notation would be that if you write that, it will be better suitable for you. That is, if I then write that is r greater than 0. So let V, what does it mean? That is, let V is a positive definite energy-like function with V of 0 equals to 0 and V dot exists and is continuous. Here you put a comma because otherwise this over the domain D, it won't be implied for both. See, here one characterization is for V, another characterization is for V dot, both over the domain D. That's why here I am putting a comma. Please try to understand. Once again I read out, let V of x from R into R greater than 0 be an energy-like function with V of 0 equals to 0 and V dot of x exists and is continuous, comma, over the entire domain D. Right? Have you now understood the meaning of R plus, R double plus? So R double plus, it actually doesn't include the origin. R plus, it includes the origin, but I wrote R plus as if R double plus. That is the reason why I explicitly mentioned V of 0 equals to 0. But anyway, to avoid that confusion, now I have written R strictly greater than 0. That means here 0 is not included, okay? And here I believe a better version would be V dot of 0 equals to 0. Isn't it? Now, the third one. We often think, like you often think, that is the global asymptotic stability. Is that not at all possible to write? No, it is possible to write, but we have to impose some further restriction on the V function. So how can we write it? This is probably going to be new for you. The origin is globally asymptotically stable. Now you see no bracket, because this is not a redundant fact. This is a special special case. Globally asymptotically stable if V dot x less than 0 for all x belonging to D excluding the origin, comma, V dot of 0 equals to 0, and the third point is completely new to you. Vx is a radially unbounded function. This part is new to you.
Is it like a convex function?
Strictly convex. That is, but strictly convex function is an example of a radially unbounded. Okay. That is a x transpose px with p positive definite. That is an example of strictly convex. Why? Because if you draw the graph, it will be exactly like this, where this is the only minimum. So only one minima, that is global minima as well. That is the one example of strictly convex function. Now this radially unboundedness, that we have to understand. First of all, I would like to see you from the book so that you have an understanding. But I don't know whether this is this book or not. No, we done. $62, right? Take what as well. I I would like all of you to see this one. I will explain, but first you check that one.
So problem.
This example, this one, v of x, that is in the book. They have taken an example, v of x equals to,
V of x equal to x1 square whole divided by 1 plus x1 square plus x2 square.
You please compare this v function with this. Okay? We will gradually understand what is radially unbounded, but first you just compare these two. You can ask that itself, compare in which sense, that is both of them are some functions. You compare whether both of them are positive definite, that is one thing. Like those three properties, whether both the functions are positive definite or one of them is positive definite, other one is semi-definite. Second one, whether both of them is 0 at x equals to 0. And third one, the most important thing, that is whether Vx goes to infinity as x goes to infinity. This is related to radially unboundedness. Let us take a small break. Third one is about the radial unboundedness. Okay. Now, what do you exactly mean by this term? Radially unbounded function.
Radially means radius wise.
Good. Then
Unbounded means the R should be infinity, or it should not be closed curve. It should be open.
Infinity in any R equals to infinity in any direction of R. In all directions.
that means when here the question is whether V is a radially unbounded function or not. And radially unbounded means what is the argument of the V function? X. Now that is how it is related to R. That is when we are here, what did I write? The radially unboundedness means that is like what is the situation for Vx as norm of x tends to infinity. Now norm of x means root over x1 square plus x2 square up to xn square. That is nothing but the radius if you restrict up to 3 dimension. Like in case of 2D, root over x1 square plus x2 square, that is nothing but r in case of a circle. If it is 3D, the same thing, it will be the radius for a sphere. Now if the same concept is extended to n-dimensional cases, then you can consider there's a r that resembles the norm of x, right? Now the question is, if that r goes to infinity, that means if the values of this norm x goes to infinity, that means all the components are together increasing towards infinity. Then if the V also goes to infinity, in that case that type of V function is called a radially unbounded function. But just whatever I said, from that your concept will be only 60% clear if we don't have this example. Why? Now you come back to the second one. Like suppose x1 and norm of x goes to, suppose norm of x is going to infinity, right? That means norm of x is root over x1 square plus x2 square, right? For such kind of functions, if norm x going to infinity means the individual component is also increasing towards infinity, right? If the x1, x2, all of them are going towards infinity. For such cases, Vx is also going to infinity, it is very fine. This is a radially unbounded function, right? Now, before you write, just you consider the first one. What happens? Like, can anybody tell me that is for the first function, when does it go to infinity? Even if only x2 goes to infinity, Vx can go to infinity. right? So and also you see that is here, if it happens that is an x1, suppose like the value of x1 and x2 both are increasing, but the first term x1 square by 1 plus x1 square, that is not contributing towards infinity.
Tends to 1.
So this kind of function is not a radially unbounded function. That is the difference. I will explain again. First you try to understand yourself.
The whole v of x tends to infinity when norm of x tends to infinity.
But in that case, even if norm x not goes to infinity, but only one x can make v2 go to infinity.
So both components should tend to infinity.
Exactly. That is the concept of radially unbounded function. That means that is this v function, it will go to infinity when all the individual x components will go to infinity. If that is the condition, then it is radially unbounded. Otherwise not. So in the first case, what happens? Even if norm x doesn't go to infinity, v of x can go to infinity.
Component means to different part of the equation.
No, component means x1, x2, xn. Those are called components. So radially, once again, that is a radially unbounded function means when that is norm x tends to infinity, we will also tend to infinity, right? But in the first case, that's why in most of the books you will find that this example is portrayed. Why? Because this is one of the very stunning example, which is an example of a not radially unbounded function. Why? Because here, even if that is x1 doesn't go to infinity, but only x2 goes to infinity, then which will lead to v infinity. So suppose if you see that is v of x is going to infinity, like mentally you will have a feeling that is okay, v is going to infinity, that means both the x components are going to infinity, which is false. In such cases, even if only one of them goes to infinity, v will go to infinity. So that's why the first example is not a radially unbounded function, whereas the second one is.
So we should look at the problem as backwards, like if v of x tends to infinity.
And also that is one more thing you see, that is this one, that is x1 square by 1 plus x, this example, you cannot express in the form of x transpose px with p positive definite. That is one easier thing to test. Because if you can express in the form that is x transpose px, then that is the safest choice. But as I said, that is for LTI, that is a brilliant choice, but not for all non-linear system that choice will work. So that's why you can see that this is a second important observation. In the first example, you cannot express in the form of x transpose px. Although the terms are in the quadratic manner, but still since it is a kind of a divided by term, so it is not only the square non-linearity, but it has not only the quadratic terms, but it is some form of other non-linearities mixed up. So you cannot break it in the x transpose px form. Whenever you see, that is why that people like this x transpose px so much, because I think you have already understood. If it is in the form of x transpose px, now you see, everybody please look into the board. The x transpose px, we already knew this, that is, and suppose here p equals to p transpose greater than 0. What is the Rayleigh's inequality? That is this whole thing. Rayleigh's inequality means this lambda mean of p. This means simply x transpose x, okay? That is lesser than equals to x transpose px is lesser than equals to lambda max of p and then x. This is called Rayleigh's inequality. Now you can easily understand that is here. If I say that what is my x2, that I think everybody knows, still for your convenience I'm writing. Simply it means x transpose x. Here everything I am considering on the real line, on the real Euclidean plane Rn, that's why it is x transpose x, otherwise if complex entries are allowed, then you have to write x star x, okay. Anyways, now this is x transpose px, that is the lower limit, that is the higher limit. Now lambda mean of p or lambda max of p, that is a constant number and that is a finite number, right? Now radially unboundedness means when that is this norm of x is going to infinity, right? So now you see, that is if norm of x, if this goes to infinity, then where does the upper bound tend to? Infinity. That's why this kind of choices is always the most favorable for us. Are you getting? Not only that it gives a positive definite function and then v of 0 equals to 0, also about this radially unboundedness feature. But the problem is, as I mentioned repeatedly, that for LTI systems, mostly this choice will work, but for many nonlinear systems, this may not work. Maybe one component, it is fine, but you have to include some other components as well. Okay? So, have you got this one? This is called Raddatz inequality. Why I used it? Because you can see this is the upper bound, lambda max of p, this is the eigenvalue. Now for p positive definite matrix, this is a real number and positive number, but finite positive number. Now if your norm x tends to infinity, upper bound tends to infinity, that's why like this function, this is a radially unbounded function. So that is here, that is at this moment, that is we have learned the theorem, but we have only understood it like the three statements, right? When we will take up specific examples, like in the Khalil's book only the examples are there, we will learn one by one. There, after solving those specific examples, you will understand that is why this fact is important. At this moment, you have understood three statements and the definition of radially unboundedness, but we still don't know, or we still haven't yet understood that why this radially unboundedness condition is required to establish global asymptotic stability, right? So unless we solve a specific example, that is, we don't. So there in Lyapunov, there are like many examples, so one by one we will learn, don't worry. Your homework is, you see the example number 3.6, that is the example for simple pendulum. So that is one of the benchmark problems. So for simple pendulum, they have shown that is if the friction term is not there, then that is it is not a stable system, marginally stable system. If friction term is there, then it will become asymptotically stable, but which is difficult to prove through a Lyapunov function, because again the question will come, that is how you will choose the p function. So these two pages, next day I will take up this example. So pages 63, 64. Okay, these two pages you please read thoroughly and multiple times. Okay, and now that is I am going to give you a small example, because otherwise it will be very complicated. So that I can show you now. Any small example.
LC oscillations.
But that is, LC oscillator, that second order, but that is only sustained oscillation, right? We can take even a simpler problem. Like suppose if you consider a transfer function g of s equals to k by s plus p. Very simple. We start with the simplest one, k and p greater than 0. Okay. What will be my state space? A equals to 0, 1 minus p0, right? I am writing in the controllable canonical form so that it becomes easy, and c equals to why I am writing in the second order form? So here A right? Okay, because in the first order system, I have to try to find out the v dot, right? V dot means directly, that is you can find, that is 2x x dot.
How do you choose that energy function?
Only one state. So if you consider the x square, then it is instantaneous power, and then if you integrate, that will give you the energy.
You do one state, we are choosing
First order system, only one state. That is the reason. Now, if it is x dot, then it is, how would you write? From that, what will be your state variable representation? X dot equals to minus bx, right? Minus bx plus u, and y equals to kx. We have to do the analysis for the unforced system. So u identically 0. So u term goes away. So you have only x dot equals to minus px. So here what happens, like 2x in place of x dot, what would you write? Minus px. So it is becoming minus 2p x square. P is positive, right? So this is less than 0 for all x not equal to 0. This is not only asymptotically stable, this is globally asymptotically stable, which is very clear from this expression, right? बेबी इस बार का एग्जाम्पल तुम सॉल्व करोगे। अभी एक एग्जाम्पल यू विल सॉल्व। Isn't it? x1 isn't it?
Shouldn't consider that UI.
And here again the same thing. Originally the system has of course U, but for the Lyapunov analysis we are making it unused. Okay. Now this is about like, are you confident that is or did I make any mistake? So this one minus p1 x squared, that is we are very happy with negative definite, right? But now these are cross coupled terms, right? Somehow, that is, if we can cancel out this form immediately, that is, it will be minus like p1 x squared. Okay. So what we can do?
We can transfer it to a x transpose px form.
Now px, that means here we have to take a different coefficient. Only that much. Are you getting? That is, if we have to cancel out these two terms, that is here now this is 1. 1 is not equals to p0. So here also if we had a p0 here, then that is we would have done with that. Then that is how we can choose that.
So we can just
Not x1 square.
half of p naught x1 square plus
Not
x2 square.
x1.
Exactly. Half of
P naught
Not
x1
x1
square.
square.
half of p naught x1 square plus x2 square. If it is so, then you will find that is these two terms will get cancelled down and it will be left with minus p1 x2 square. But should it be the ultimate result? Suppose even if that is it is p0, they are cancelled out, so we are left with minus p1 x2 square. Can we say that it is negative definite? Why? Because it doesn't have any contribution from x1. So in this case also, we cannot call this is negative definite. This is actually case of negative semi-definite. So from that, local asymptotic stability is guaranteed, not global asymptotic stability. That is, we have to think about that how we can further adjust the v function, right? So that part you think, next day we will take up that. Isn't it interesting? So that's why I wanted to take that example. In the first order, there is no possibility of any confusion. But you see, this example, this is also very simple. Just a second order plant with a complex conjugate eigenvalues. Still, that is, we have some issues. Are you getting here what is happening? That is, even with the v dot function also, you might think, that is, when I was a student, I also many times I used to think, that is, finally we are getting minus p1 x squared. Like for all like is a non-zero x2, that is, it will be like negative only. What is the problem with?
For all x1, x vector we should get.
But here what is the problem? The way we have defined the v function to be a quadratic function, exactly in the same way, this v dot x, that should also be that we should also try to express v dot as a quadratic function. So here also it would be like that is x transpose qx. Okay, and if this q is negative definite, then originally it would be a negative definite v dot. here what is happening when you have this minus p1 x2 square, if you wish to express in the quadratic form, then what will be that Q matrix? It will be simply 0, 0, 0 minus p1. Now it will be clear. It is not a negative definite matrix, it is just a negative semi-definite matrix. That is the problem. So now your home task will be to find out that which V, like something whether should we add or so that we can establish that it's a globally asymptotically stable. Okay? This is the concept. This point is utterly important because here many people, especially the beginners, we make mistake. That is by seeing that ultimately V and V dot both is a scalar. So as a scalar value you see this is negative. So why can't we say that this is negative definite? That confusion always occurs. So that's why that is I express this in the quadratic form from which it is clear that this in between the matrix Q, this is not negative definite, rather only semi-definite. Okay? बोलो सर पॉजिटिव डेफिनिट कैसे हम लोग फाइंड करेंगे? इसी एग्जांपल पे v फंक्शन को हम लोग कैसे चेंज करेंगे? जो होम टास्क अभी मैंने दिया ये dx को ज्यादा टफ नहीं है, बस वही उधर सोचना है कि हाउ कैन वी गेट एन एप्रोप्रिएट v फंक्शन व्हिच विल लीड टू नेगेटिव डेफिनेटनेस। तो उससे हम लोग को सामने क्या आ रहा है जे इधर देखो that here we have only x1 some x1 square and some x2 square, but we didn't consider any cross coupled terms x1 x2. That is the reason why we are not getting any contribution from the x1 square. That is one of the things. So in that sense, you should try how to find a peak. So here the problem lies with how to find the P matrix. This is the easiest choice. That is when in the most of the books or even the here you will find that is okay half x1 square plus half x2 square. Why they choose like that? When you take the derivative, like 2.5 gets cancelled out, simply you will be getting x1 into x1 dot. So that is the easiest choice. But here you don't have any cross coupled term. So ultimately you see that is here the problem that we are facing. From that also, that is, we have understood two other things. That is, the Lyapunov is a sufficient condition, right? See, with this V function, we are not able to conclude that it's asymptotically stable system. But originally, it is asymptotically stable system. That is the facts I told you on the first day. That is, with the V function, if you can't reach the asymptotic stability, you should not you cannot conclude that the system is not asymptotically stable. With this V candidate, we are not able to show the asymptotic stability. We have to find a better V. Okay? And this is also the reason why the Lyapunov is a sufficient condition. Again, you can have a doubt, you can ask that is, sir, you only told that is like Lyapunov is a necessary and sufficient condition for the ATI system, then why are you like withdrawing your word? This is with respect to the V function. Which condition is necessary sufficient? When you are using that matrix equality condition PA plus A transpose P equals to minus Q. That check or that theorem is the necessary sufficient result. But when you go to the first principle approach, that is choosing a function V and then checking the V dot, that is still sufficient. Okay? These last 3 points, these are highly important. Please like keep a note on your own words, okay? Okay guys, thank you. After that, if you have any doubt, please feel free to post on our WhatsApp group, okay? If you have any doubt related to the Lyapunov or anything. And don't forget to check that example 3.6.